I'm going to try to get, we might quiz on this later in the week, but we need to get through Polar and we need to be basically done with everything by Friday. Okay. So we might go a little less on quizzing and a little bit more on pushing through the stuff because we just need to get done. So that gives us 3 full weeks of review when we get back from break. Okay. Because I think we need that. Anything that we need to like re-quiz, we will do as like part of, I'll give you like free response question quizzes, and whatever topic that covers, we will make it replace a grade if we need to. Okay. If you have missed quizzes and stuff, and I know I haven't done a whole lot of getting the grades in the grade book, but if you've missed stuff, you need to make sure you're getting in here and getting it taken care of. Okay. Technically, the triad doesn't end until we get back from break. All right. But you don't want to push it all into that week. So if you've got anything you know you need to make up, I'd get in here this week and get it done. Okay. All right. So we're talking about motion along a curve. Go ahead and read that example to yourself, please. Okay. We've got a particle. It starts at rest from the point -1, 2. Okay. With an acceleration vector of a of t equals I plus 2j. Find the location of the particle at t equals 2. Could we go back and pull out I am very proud, dude? Could I still use that strategy? Even though we're in vectors or parametric or whatever you want to call it, because basically vectors and parametric are the same thing. Where am I starting? What do I have, the information I have to begin with? Acceleration. Okay, where do they want us to get to? What's location mean? That's position, right? So I'm going to position. So that means I need to do what? Integrate. So wherever it's coming from, remember that's what we're doing, integrate. I need to integrate how many times? Twice, okay? So we have to get our velocity vector first. And so this is going to look a little bit different than what it did before, but we're gonna go with it. So I'm going to find velocity vector first. I know I need to integrate I plus 2j dt. Okay, so remember the I and the j, they just kind of get tacked on to the end of everything here. So my I part of the vector, or my x component of the vector, when I integrate just the 1 that's there, what do I get? Not 0. If I integrate that, what do I get? Stephanie, say it louder. T, you get t. Don't forget the easy integrals, you guys. Right? 1 dt goes back to t. All right, and then plus, when I integrate 2 dt, what do I get? 2t. Oh, I totally blew something here. Technically, it's t plus c times the I vector. And I put c sub 1 because we're going to have more than one c. Plus 2t plus c sub 2 times the j vector. You have to add your constants in there as if we're integrating these two components separately. Okay. It's not like when we did like the separation of variables, you only put the plus c on one side. You have to put it in both places. So we need to figure out what those c values are. It's hidden right in here. The particle starts at rest. What's the velocity when the particle starts at rest? Yeah. So this means that the velocity is 0. Which means that I'm going to set both components equal to 0. Okay. So really what I'm doing, I'm going to be really bad about this. I'm going to squeeze it in here. I know that it's 0i plus 0j. I'm going to solve for each one of those components to find my c values. It's going to seem silly because it's all zeros, but this is the process in case it wasn't. They may have given you some kind of velocity in there. All right, so I would take the t plus c sub 1, set it equal to 0. No, hang on 1 minute. I did not do that right. Nope, that's not what I'm supposed to do. I know my velocity at 0. That's what I did wrong. I have to write this on a separate line. Don't copy Mrs. Ballard right now, apparently. All right, so we have to actually put our velocity at 0 in there. So we know our velocity at 0 means that when I have time 0, my I component plus 2 times time 0, C sub plus C sub 2 times my J component equals 0I plus 0J. It's trying to take it, shortcut it too much. That's a 1, not an I here. Okay, so what that means is 0 plus C sub 1 equals this 0 for this I component. I just scribbled something weird. So this is here equals that part. Okay. All right, and then this piece here equals this part. So 0 plus C sub 2 equals 0. So what are both C sub 1 and C sub 2 equal to? They're both equal to 0. It was a lot of work for a whole lot of nothing. But it's important just in case it was something other than 0 there. Okay, because it could be. All right, now I need to get to position. I'm just looking at what they used. They used an R. It doesn't really matter what variable you use. So they called their position function R of t. But it doesn't matter what you use. If you wanted to use P of t or X of t, you could. All right, so that means I'm going to integrate my new position vector, which is t I, right, plus 2t j dt. So what I did was I grabbed this part here, because we know C sub 1 is 0, and that part there with the I and the j. Rather than writing it twice, I wrote it out once. And obviously I wrote way too big. Okay, I'm going to just move my work out here so like we can see it. All right, we're going to go ahead and integrate. So when I integrate t, what do I get? T squared, so this is R of t, equals t squared over 2 plus C sub, actually we have to go another one, C sub 3, because technically you already had C sub 1 and C sub 2. And then times I plus, okay, now I need my J or my Y component. When I integrate 2t, what do we get? 2t squared over 2, which is really what? T squared. So t squared plus what? C sub 4, good, times, you just keep following the pattern, right? Times J. Okay. Then I need to put in, I'm looking at what we subbed in here. Yeah. Yeah, you can have sticky notes. Absolutely. What did I do with my stuff? Anybody else needs a sticky note? We've got lots. Thank you, Noelle. All right, everybody got it? Okay. All right. So now we need to solve for our C sub 3 and our C sub 4. Okay. We're going to use kind of our initial condition. When we are at rest, what's my component there? negative 1, 2. So that means when I plug at time 0, I am equal to negative 1i plus 2j. Okay, so let's plug that in the way that it looks. So when we're at 0, so that means anytime I see time 0, I'm plugging in a 0, plus c sub 3i plus 0 squared plus c sub 4j equals, what did we say it was? Negative 1i plus 2j. Negative I plus 2j. Okay, so that means that this piece here is going to get set equal to this one. So we'd have 0 plus c sub 3 equals negative I. Sorry. Negative just equals negative 1. I don't need the I part, so negative 1. It's kind of like when we did partial fractions. We did partial fractions when we set like just pieces equal to certain pieces. Similar to that. All right, and then this piece is going to be set equal to the 2j, so I'm going to do 0 plus c sub 4 equals 2, which means c sub 4 equals 2. All right, so now I'm going to go and I'm going to write out my position vector. Okay, so I'm going to go just like when this was basically when, remember, we did the particular solution problems. This is the particular solution type problem for vectors. We're going to go back into here and substitute in c sub 3 and c sub 4. So r of t equals t squared over 2 minus 1i plus t squared plus 2j. That's my position vector. All right, I want you to go back now and read the question. So read the question. Have we answered the question yet? No, what do I still need to do? Good, we got to plug in the 2. I'm glad it's obvious. Okay, that's really good. All right, this stuff isn't that hard, right? It's just we're adding this extra weird component piece into it, right? It's the same stuff we've been doing. It's just we added the layer of vector to it. All right, so we've got 4 over 2 minus 1i plus 4 squared plus 2j. So let's see. 2 minus 1 would be 1i, right? Plus 4 squared is 16 plus... Is it 2 squared? Yes, it is. Thank you. All right, 2, and where did I get the 6 from? My goodness gracious. That was interesting. So 2 squared plus 2 would be 6. I probably copied the wrong thing down. I was looking at the answer key, so it was probably I just copied the wrong button off the answer key, or wrong thing off the answer key. All right, so I would probably conclude it by saying at t equals 2, the particle is at point, and you can just write it as 1, 6. So I'm going to scroll that up for you a little bit there. Write what you need to write. Okay, got it? All right, read the next one to yourself. We might need more sticky notes, so write small. Start by writing small. Okay, hopefully everybody's got an extra sticky note. Okay, let's take a look at it together. So a particle with an initial velocity I plus j, or vector I plus vector j, and initial position 1, 1 has an acceleration vector a of t equals negative cosine t vector times vector I plus sine t times vector j. Find the location of the particle at t equals pi. So if I did my I am very proud dude, where am I starting? Acceleration, where am I ending? Position. So what do I have to do? I got the calculus I need to do. What calculus I need is that I need to integrate. Okay. So I know if I'm going to get to position, I have to start with velocity. So velocity at t is going to be the integral of negative cosine of t times vector I plus sine of t times vector j, and then dt. Okay. When we integrate cosine, negative cosine, what do we get? Negative sine, good. Plus c sub 1. And then times the vector I. And then plus, when I integrate sine, what do I get? Yep, negative cosine of t plus c sub 2 times vector j. Okay, they threw us a couple of things that are different than what we did in the last one, okay? When we see initial velocity equals I plus j, what that means is velocity when time was 0 is 1I plus 1j. Okay, so initial velocity means the time component is 0, because you need to know that for what do you plug into for the t, right? When we have to try to solve for the c sub 1 and the c sub 2. All right, so I'm going to go v of 0 equals, and I'm going to plug 0 into this, and then set it equal to the 1i plus 1j. So negative sine of 0 plus c sub 1 times vector I plus negative cosine of 0 plus c sub 2 times vector j. We're going to set that equal to 1 times vector I plus 1 times vector j. It's up to you if you write the ones or not. Okay, so now I'm going to set each one of these components equal to the 1 or the I. So I'm going to use this one here. What is if I go back to good old unit circle, right? What's the sign of 0? 0. So can't I just write c sub 1? I really don't need to write 0 plus c sub 1 or plus c sub 1. And that's going to be equal to what? 1. Good. All right, now I'm going to look at this component. What is cosine of 0? So I'm going to end up with negative 1, correct? Plus c sub 2 equals 1. So what's c sub 2 equal to? 2. This is a little bit more interesting than last time, right? We got those silly zeros last time, so it didn't make a whole lot of sense what we were doing. But now hopefully you're seeing it can be something other than 0 there. So it's going to be integrate a little bit differently on our position function. Okay. All right. I'm going to draw a little bit of a squiggle there because that's all just getting to velocity. Now I'm going to get to position. I'm going to write my new function. Okay. So inside my integral, I'm writing my new function. My new function is, remember, I'm going to use this and plug in c sub 1 and c sub 2. So negative sine of t plus 1 times vector I plus negative cosine of t plus 2 times vector j. And then dt at the end of the whole thing. All right, we got it. Okay, so let's go ahead and integrate again. When I integrate negative sine, what do I get? Cosine, good, of t. When I integrate 1, what do I get? T, and then what do I also have to put? C sub 3, right? Times my I vector. Plus, when we integrate negative cosine, what do we get? Good. When I integrate 2, what do we get? 2t, and then plus c sub 4 times vector j. Give you a minute to catch that up. I'm going to take mine off to the right side here because I ran out of space. Okay, so I am now going to look at my initial position. So look at initial position. It's pretty much the same thing as the initial velocity, right? So r of 0 is 1i plus 1j. Which is really the same thing we had with initial velocity. They just stated it in 2 different ways. Okay, so let's use that fact. So I'm going to go r of 0 equals. Anytime I see a t, I am plugging in a 0. So cosine of 0 plus c sub 3 times I plus negative sine of 0 plus 2 times 0 plus c sub 4 times j. And we know that that's going to equal 1i plus 1j. I really should be saying vector j and vector I. Okay, unit circle again, right? What is the cosine of 0? 1, good, plus c sub 3 equals 1. What's c sub 3 equal to then? Oh, 0. All right. What's sine of 0? 0. So 0 plus c sub 4. What's c sub 4 equal to? Yeah, just the 1. Okay. I'm going to rewrite my function, and then I'm going to go back and read my problem and make sure I've got what I wanted. Okay. I'm going to rewrite, and I'm going to rewrite based on, let me zoom out, this line right here. Okay. So I've got cosine of t plus 0, right? Times vector I plus negative sine of t plus 2t plus 1 times vector j. It's vector j. Do you see why I put a tail on my t's? Because it looks just like a plus sign otherwise. It's right next to it. Okay. Go back and read the question. What are we supposed to be finding? Yeah, have we found that yet? No. So what do I still need to do? Plug them back. They're not hard problems. They're just long, right? It's just a tedious process. Okay. All right. So r of pi equals cosine of pi plus pi times vector I plus negative sine of pi plus 2 times pi plus 1 times vector j. I've written the unit circle 3 times now in this problem. All right, so this is the coordinate for pi. What's the cosine of pi? Yep, so negative 1 plus pi times the vector I. What's the sine of pi? 0, so I just end up with 2 pi plus 1 times vector j. And then it doesn't hurt to conclude with a sentence. So at t equals pi, the particle is at point negative 1 plus pi, comma, 2 pi plus 1. Okay. I'm going to give you a minute. I want you to read this next. Actually, I want you to read this little guy right here. And then read, and I know there's a calculator there. Don't worry about that part. I'll pull mine up. And then read the problem, or skim through the problem really quick. Okay. So I'll give you about 2 minutes to read all of that. Actually, if you want to grab a calculator, grab a calculator. If you don't have your own, come grab one of mine, okay? So I'm looking at what we have to do, and it's a good thing to practice. Okay, let's take a look. All right, so why this is a nice to know versus a need to know. They will not typically expect you to know the gravity equation, okay? So this equation they gave you is like the object with gravity applied to it equation. And it's negative 16t squared plus your initial velocity times t plus your position at 0, okay? If they're going to give you a position, velocity, acceleration, they're going to be very explicit and give you whatever the equation or the function is. Okay. So you can solve some of our parametric equations or our vector equations here using or starting with that. Okay. That gravity equation. All right. So we've got a baseball. It's hit from 4 feet above the ground and leaves the bat at a speed of 105 feet per second at an angle of 40 degrees to the ground. Okay. So we add in the vector piece. And so I'm going to kind of just teach you the process here. Again, you probably won't see something like this one in particular on the PTEST, but there's some concepts in there that are good that could pop up. All right, all we have to do is write a vector that describes the motion of the ball. So we're talking about our position vector, okay? So I'm going to start with R of t equals. All right, which means what I am trying to find is my x component times I plus my y component times j, which I probably don't need to write that, but that at least gives you a little bit of a, hey, I know I need to find an x something and I need to find a y something. Okay, so the x component is only going to involve the velocity piece. Okay, so you're only going to look at what's going on here. Okay, I want you to think about back to unit circle. Okay, when is your x value your sine or your cosine? Cosine. Okay, so what we do to get our x component here is we take our initial velocity. What was the initial velocity? 105. So 105. Okay. And then we multiply by our cosine of our angle, which is 40. And then we multiply by t, because the t that's from here. And then that's our I component. Now I need to get my j component. My j component uses the entire equation because that's going to be the height. Okay, so it's going to use this entire thing, which would be, it would be negative 16 t squared plus this same initial velocity, except that in the y component, am I sine or cosine? We're sine, right? The unit circle would, from unit circle would be sine. So I would say 105 times t times the sine of 40, and then plus my initial position. What was the initial position here? 4. And then times j. Okay. No, it's just for, I have a parentheses in the wrong place. Good job. It shouldn't be there. It should be there. Okay. But good eye. I was parentheses happy, wasn't I? I guess I could have put the 40 in parentheses. I don't have to. I try to sometimes when it's complicated use less if I can. All right. We're going to go in the Wayback Machine now because it's been a long time since we've done this next part. We're supposed to determine how high the ball goes. Okay. How high is a maximum, isn't it? So we're talking about when is the ball right there? Okay. It says determine how high, but we're really talking about, the answer they gave me was in time. I'm going to rephrase that question just a little bit. I guess I could find determine how high, because I could put it back in the equation, I guess. We're going to at least find the time. Find time of the max height is what we're really going to do. So if I have position and I have a maximum, I need to find the maximum. Okay. Where do maxes and mins come from? Think way back to sine charts. We haven't done those in a while. Say it again. Stephanie? Okay, we do hit, if we're going to do an absolute max, we do use a candidates test. We're not asking about an absolute max. We could just use relative. When we do a candidates test or we do a relative max or min, what do we need to use to find that? What calculus do we need? Yeah, there we go. We need to take a derivative, right? Now, which one of those components has to do with the height? The j, right? The y part of the component. So I'm going to take the derivative of the y component to do this. Okay. So y prime of t equals. So we're looking at this piece right here, and we're going to take the derivative of it. So what is the derivative of, looking at what they did, this first, look, oh, they wrote it backwards. Okay, what's the derivative of negative 16t squared? Negative what? 32t, perfect. Okay. And then this is kind of weird, right? This is a number, this is a number, so that's the coefficient. So the derivative of that thing is just what I highlighted in yellow, right? So it would be 105 sine of 40. And then what's the derivative of 4? 0. Good. All right. Now that I have that, I'm going to make it bigger. So you think we need it bigger. What is the slope at a maximum? It's 0, right? So I'm going to set this equal to 0. Okay, so that doesn't look too horrible, I hope. We're going to get it put in our calculators here in a minute. How am I going to take this ugly number and put it to the other side? Good, subtract it. I'm totally not writing the right thing. 32t equals negative 105 sine of 40. And then what am I going to do with the 32? Divide. So I've got negative 105 sine of 40 over negative 32. All right. Let's see what time our slope is at a maximum here. Okay, so let's go ahead and put this into our calculator. And I could just do that. I don't have to put it in the graph, I guess. I could just do that right off of this page here because we kind of solved everything for it. Make sure you're in radian mode. And I'm going to do a control divide. It's negative 105 sine of 40. And then we're dividing by negative 32. Uh-oh, I got a different answer than they did. Did we agree with me? Yeah. All right, we'll go with our answer. Maybe we might have a sign error. Hang on. Let's see. No, I don't see a sign error. They have sign error. They got negative 32. Oh, wait a minute. It should be no, wait a minute. But we divided it. Oh, my 105 should be positive, shouldn't it? Because I subtracted it over. So it doesn't matter. Pick one of them to be positive. Let's try that. I don't know that that's really going to change it much, but one of them should be positive. I'm going to try copying and pasting. Oh, should it be cosine? No, it's sine. That part I'm positive of. It was the negative in front that I think I'm off on. Still got the same number, but a negative now. Which doesn't make sense because it should be positive time, shouldn't it? Oh, duh. It should be cosine. You're right. It should be cosine. What happened? Yeah, they have I was copying the answers and I totally write the. Let's try that again. Okay. All right. Okay. So we should have cosine of, it was t, right? Because derivative, you're entirely right. When we take the derivative of sine, it should be cosine. Oh, no, wait. That's just a number, though. So we don't take the, it's a no, it's still sine. Okay, so here's the reason why. Okay. This is there's no t, right? It's a number. So we would keep it sine of 40. So I think our number is just off of the answer key, which is okay. It sometimes happens. Sine of 40. We're all human and we all make mistakes somewhere. So the only thing I saw that was different, they got a positive. What did I do wrong here? Oh, you know what? Maybe I wrote it wrong. Nope, positive 105. They put minus 32t. We did our arithmetic and they did it all on their calculator. So, all right, we're just going to go, what was it? T equaled, we're going to go with the positive answer though, not the negative answer. I lost my calculator. There it is. 2.444. Okay, let's go 2.444. 2.444. All right. Now, technically, that's the time that the ball goes the highest. What would I have to do to find the actual height? Yeah, and where are we going to plug it into? Wouldn't we have to go plug it into the y component? So we would want to do y of the 2.444, whatever it was, right? Equals negative 16 times 2.444 squared plus 105 times 2.4444, whatever, sine of 40 plus 4. Okay. Let's take a look at putting that in. Okay, so I have totally lost my, it's got to go into that one there. So I lost it. So negative 16, 2.44. Okay. So negative 16. Ooh, not that. Negative 16 times. And I'm going to grab this and copy it so I get my most accurate answer. Oh, look at that, even more. Squared plus the 105 times that decimal point again, sine of 40. Remember, you got to use the trig button. It doesn't like it if you don't use the trig button. Sine of 40 plus 4. Something's not adding up. It shouldn't be negative height. Is it supposed to be a negative what? You copied the negative one. Oh, I copied the, you're right, I did. I should have grabbed the positive one. That would have made a difference. But it doesn't make a difference on this component. But there we go. 99.641. Or 640, actually. We'd like to top it off. 99.641. Whatever this was in. Feet. All right. Part C says there is a 12 feet high fence 325 feet from home plate. Is the ball a home run? Meaning it does at 325 feet, does the ball go? Is the ball more than 12 feet high? Okay. So this is talking about the horizontal distance. It's talking about x of t being 325 feet away. So I need to take my x component, the position component, and set it equal to 325. So we're actually not really doing much calculus. We're taking our x component and setting it equal to this. So I'd have 105t times the cosine of 40 equals 325. All right, so we're going to put that in our calculator again, right? So we would have 325 divided by 105 cosine of 40. All right, I'm going to grab that really quick. So control divide 105. Look at what I have to do. 325, not 105. 325 divided by 105 cosine of 40. Yeah, we're still not getting the same numbers there for some weird reason. I wonder if it makes a difference if I do this, because I'm noticing a degree symbol on there. I'm just going to play with something. It might be a degrees radians thing that's weird. Did he use the degree button? Let's try that. Yeah, that's what it is. Okay, that's why we're getting different answers. All right, this is why this isn't on the AP test. Can you see? Because we typically work in radians, right? This particular problem, you have to do it in degrees. But do you see how you could leave your calculator in radian mode, and all you have to do is grab the degree symbol? So we would grab this. The degree symbol is hiding. Sorry. It's hiding under the pi button right there. So you just add that on it. Now I have the same answer that they do. So that's totally my fault on the first one. We'll fix it here in just a second. Okay. So we would be at time 4.040. Okay. Probably with the 5 on the end. All right. Let me get back to my right thing here. So that means that time, we want to probably add the degree symbol there. So time is approximately 4.0405. Makes more sense why I wasn't getting the right answer now. All right. So I'm going to now take that. I need to figure out the height. Is the height the x component or the y component? It's y, right? So I'm going to plug this t value back into the y component of this and see if I make it more than 12 feet. So we're going to find y of 4.0405, which is the, whatever this was, negative 16 times 4.0405 squared plus 105 times 4.0405 times cosine, it was cosine, no sine of 40, plus 4. Okay, once you've got it written, go ahead and put it in your calculator. Use the copy and paste feature. Okay, make sure you get the most accurate answer. Yes, use 40 degrees. Let's put the degree symbol in there. And then we'll go back and correct our other one if we've got time. We might not. What time do we get out? 11. They're going to probably come on with announcements here pretty quick. So we might not be able to correct the other one. But at least we know why it's wrong now. No, it doesn't like that. for? Everybody go to 15.491. We good? Did they make a home run? Yeah, so 15.491 home run. The 12, it made it over the 12-foot fence, so therefore the ball is a home run. So the hit results in a home run. And I think that's where we're going to end it. Okay. We know we need to go back in here and we should really still edit this 40 degrees. This time would have been different. It came out to be on there as 2.10915. So this answer here needs to be edited. So, and make sure we do 40 degrees there. So that answer isn't correct. And they didn't actually finish the answer. So, all right. Tomorrow we get to start working on polar. If you have it and you don't want to borrow mine, I bring your calculator the next couple of days. Okay, so you're practicing. I know it means silly, but you want to practice with yours. Sometimes we just our comfort levels with ours.